again. Our next speaker is Romeel. Please take it over. Oh,
She's got the USB thing for that stuff.
Sandy, is it
Oh.
USB?
All right. Wait. Let's see. That's why it wasn't working. I won't use it anyway. So. Okay, great. Yeah, well, thanks for it's really great to be back here. I haven't been to one of these in a fair number of years due to various unfortunate logistical issues. So it's really nice to be back and see a lot of new faces as well as old faces. Yeah, and I thought I'd tell you a little bit about Simba. I don't think we have any other Simba talks, so this is going to be a little bit of a scattershot talk, talking about various aspects of things, but hopefully it'll be something of interest for everyone. Most of the focus is going to be on the EOR extensions to Simba. So again, just to remind you, but probably many of you know this, we had Mufasa way back when, then Simba added all the black hole, pretty unique black hole growth, as well as a unique bipolar black hole feedback model, as well as a unique dust growth model. At the time, now people are doing similar things. And we've had a number of spin-offs, the 300 cluster zooms run with Simba, the camel simulations for machine learning with cosmology. You haven't heard too much about that, but it's a really interesting project. We have something that just got published, which is Simba-C, which is an updated chemical evolution model, has some very interesting implications that I won't talk about today, and one that hasn't quite been published yet, but we're working on it, the hyenas group scale zooms. So all of these are happening. In addition to that, there's two sort of EOR-focused ones, which I'm going to talk a little bit more about today, particularly Simba-EoR. That's also Cosmic Sands, which is led at Florida by Sidney Lauer. And in the near future, of course, we're going to have Kiara, the daughter of Simba, and that will be hopefully coming up in the next year or two. So yeah, and by the way, everything is, well, not all of this is public, but basically all the Simba stuff is public at this website, so you can download snapshots as well as very extensive catalogs that are pretty easy to use. Okay, so if I had to pick one thing, I just wanted to talk about one thing that is really different in Simba compared to all the other models, okay, before we get into the EOR stuff. So this is kind of a bit of an aside. It's halo evacuation. Okay, Simba has very strong AGN feedback. It's bipolar, unlike any other model, so stably bipolar. And it pushes out and heats gas. And you can see the temperature, just a temperature slice in TNG versus Simba, right? This is a 50 megaparsec, well, actually, 100 megaparsec temperature slice, very different, right? It really heats the IGM. Where's that stuff coming from? It's coming from, obviously, the CGM of galaxies. This is a plot of the baryon fraction versus halo mass, broken up into various CGM, or, well, this is the blue part, the purple is the stars. You can see the low values, right? This is the cosmic fair share of cosmic baryons. It's way down, right? It's like between 10 to the 12 and 10 to the 13, only 10% of the cosmic fraction is actually in the CGM. All right? This has huge implications. You can see that also in the baryon fraction versus other models. So this is for Simba, but this is comparing to Romulus, doesn't hardly evacuate at all. This is Eagle, TNG, somewhat similar. This is Simba, way down here. Agrees well with Bahamas. Bahamas was a version of Simba, version of Eagle that was tuned to match observations of this plot. Another interesting fact is you have to go out very far to get your fair share of baryons. We asked the question in Daniele Serini's paper, how far out do you have to go? The later TNG paper dubbed this the closure radius. This is a factor of 10 times the virial radius, and you're still not back to your cosmic baryon fraction, which is this, right? You actually have to go out 20 virial radii at these sort of group scale masses to get to the cosmic baryon fraction. So that's really remarkable. We thought surely we could rule this out with some observations. So far, it hasn't been true. In fact, in many cases, this sort of thing works better for a lot of observations. But I think there's some very interesting things that can discriminate in the near future, particularly SC. Okay, so that was just to illustrate that. Most of this has to do with the AGN jet feedback. Okay, so this is something that comes in at late times. the jets turn on when you get low Eddington ratios. Okay, so you need big black holes, low accretion rates. So most of this is not so applicable for the EOR, so I probably will sort of set this aside and talk a little bit more about, just introduce cosmic sands on one slide. Okay, so what is cosmic sands? So Sydney and Deshika came up with the idea of running a bunch of 25 megaparsec box, taking the largest galaxy in each one and rerunning as a zoom in that box at 64 times the mass resolution. So now you're resolving effectively every hydrogen cooling halo. Right? So this is an example at redshift 6.7 of a cosmic sands galaxy, and just to show you how awesome JWST is, as if anyone needed convincing of that, Spitzer versus near Cam and Miri, little colored plots there of that galaxy, right? So this is the galaxies in star formation rate versus stellar mass. This is, I believe, the Spiegel extrapolation at that redshift. See, most of them are sort of at, but a lot of times above that case, right? So Simba tends to produce a lot of very rapid early galaxy growth in the massive end, okay, suppresses the low mass end. Then you can look at some of these images. This is fun. It's more fun to look at these, you know, more close up, but this is stellar mass versus gas mass in this plane. You know, we tend to get, the big galaxies tend to be, yeah, fairly gas rich, as you might or have a lot of gas. Look at, these things are very disky. So we haven't quite gotten around to getting V over sigmas for these yet, but even at redshift 6, we get fairly large disky galaxies. And these things are, you know, stellar masses around, some of these are stellar masses approaching 10 to the 11. You sort of take gas mass and multiply by that, or add that. Okay, so that's cosmic sands. I'm going to spend a little bit more time talking about another suite of simulations that we're putting together, which we're kind of preliminary calling that Simba-EoR, for better of a lack of a better thing. And what's the big new thing here? The big new thing is our subgrid ISM model. So yes, in Simba we had dust formation. Yes, we had a sort of a crude model for H2 formation. But none of that was tied together. It was sort of like all pasted on and calibrated to redshift 0 stuff. Instead, we've replaced all of that with a sort of a self-consistent subgrid model built into the Grackle cooling module. Okay, so for instance, we have the dust growth and destruction. You know, it's all sort of in a circle of life, as they might say. Dust growth and destruction. The dust growth then stimulates H2 formation. The H2 formation then is used to form the stars. The stars then put out an interstellar radiation field. That interstellar radiation field then, of course, you know, sets the dust temperature and the dust and the dissociation of the H2. All this is now done sort of, you know, as self-consistently as possible. So we treat each big particle as a bunch of clouds that are all doing this in pressure equilibrium with some hotter external medium, and we have the full reaction network for the H2, okay, including the dust. So all this is now in there, right? So this you might think is fairly important at high redshift, particularly when you're sort of forming, you know, H2, and as particularly if you want to look at dust and have all these dusty galaxies that we're seeing out of redshift 5, et cetera, right? So that's quite nice. So this is all sort of the new aspects compared to our previous model. And again, this is all sort of done self-consistent. It's a subgrid model still. I mean, there are a number of parameters and assumptions. One of the nice things about this is that the dust temperatures are an output, no longer an assumption that we had to make there. Right? And I don't think I'm actually going to show this, but the dust temperatures at redshift 6 are really high, like 100 Kelvin. Yeah. Okay, so what does it look like? UV luminosity functions. One of the problems with Simba, I think somebody showed the plot earlier, but didn't pay attention to it. The Simba line was quite low in its UV luminosity compared to what the observations were. Now we're not, okay? The reason the Simba was so much lower was because our H2 model, when you extrapolated, it was essentially the Krumholtz model. When you extrapolated to very low metallicities, it really shut down the H2 formation. Much more so than we actually get when we self-consistently do it. Okay, so this is 11 through 6, and the data plotted here is this: the yellows at redshift 6 and the greens at redshift 11. So you should sort of see them moving from this to this over time, and you do. These are two volumes that we have, 50 and 25 H inverse, each with 1024 cube particles. So we're not seeing a problem here with forming very bright galaxies. I mean, this is not the very brightest things that are actually being seen just because of the volume, but at least up to the regions we can tell, we sort of mostly agree with the data. And the attenuation, so what's interesting is we have magnitudes in the UV and dust-free magnitudes, right, in our simulation. And that basically translates you rightwards in this diagram. If you compare the no dust lines with their dashed ones to the dust lines, that's roughly a magnitude in the extinction in the UV. So there's quite a bit of extinction, and all the way down to the fairly low masses or brightnesses. Okay, going to look at some mass functions, right? Stellar mass, black hole mass, star formation rate function, H1, H2, dust mass. So some observations are shown here, like the redshift 6 mass function from Song et al. From the HST data. And you say we do predict a more low stellar mass galaxies, so let's hope JWC finds them. And then the other interesting thing, okay, these are just basically lines on a plot, mostly showing pretty good convergence, maybe not so great in the gas. If you compare the red and the blue lines, the blue line is the larger box, red line's the smaller box. But overall, pretty good. Interesting to look at sort of the peak things that we're getting in these volumes, right? It's quite high. Like star formation rates of something like the largest galaxies have over 100 solar masses per year at redshift 6. Okay, large H2 masses as well, as you might guess, and fairly large dust masses. You can get dust masses well over 10 to the 7 solar masses. That's not exactly what's seen in the very, very brightest, ULERGs that can get up all the way to 10 to the 9, but again, this is a modest volume, right? So you can get pretty big galaxies growing already by redshift 6 in this thing. So you can look at some scaling relations as well. This is fun. So this is specific star formation rate, the H1 fraction, H2 fraction, the star formation rate weighted metallicity, black hole masses, Eddington fractions, and dust masses, dust to metal ratio rather. So we're getting very large Eddington, just randomly things about this. We're getting super Eddington accretion here. We allow that. Our torque limited model is a disk model. It doesn't satisfy spherical symmetry assumption of the Eddington rate. So we just from our, I didn't talk about the torque limited model, but that's a unique feature of our black hole growth model. Dust to metal ratios are pretty high already, right? Look at this. Like you can get it's -1, better than a tenth of the metals are locked into dust already by these fairly early redshifts. You can get reasonably high black hole masses, so on and so forth. So yeah, some pretty interesting things. And look at the metallicities. Right? So the metallicities approaching solar for the most massive galaxies at redshift 6. So when you say there's solar metallicity in quasars at redshift 6, yeah, no problem there. So yeah, these are all just sort of general predictions. So what can you do with this sort of thing? Well, one of the fun little projects that we've done with this is to try to use machine learning, because everyone's doing it, right? So we have to do it too. But what was our idea for doing machine learning? Well, the idea here was to actually try to extract physical properties from the photometric data. But we didn't want to just use the photometry bands. We thought, well, why not just give them JWST images, right? So you give them the whole image, right? And you give them a set of images and try to just say that, tell me what the physical properties of those galaxies are for each image, right? So what do we do? So this is work done by Qingyang Li, who is a student who showed up on my door from China one day. Really had no idea he was coming. So we apply powder day, which is the dust radiative transfer code, to our redshift 6 galaxies here in this case, create smooth with the appropriate PSFs, et cetera, create mock postage stamps for each of these galaxies, then apply the bandpass. Well, those are the bandpasses. And then use a convolutional neural network and essentially feed these images and try to essentially recover some of the basic physical properties of the system, right? So should account for all the color information, the variations in colors across the galaxy, so on and so forth. So the bottleneck in this thing is actually generating these images. It's slow. So that's the unfortunate part. And so the results I'll show you kind of preliminary because we're still generating more images and we're finding that the more images we have, the better the results so far. But here's some of the images, or the results rather. So this is just from 6-band Sears photometry. Okay, so if we apply sort of the band passes, et cetera, for Sears, this is how well we recover stellar mass, star formation rate, metallicity, H1 mass, and H2 mass. Okay, so this is basically the predicted value versus the true value, the ratio of those two things. And of course, ideally, you would want everything, tightly around this one-to-one line. And in fact, the nice part about it is that we get generally pretty unbiased recovery, right? That's always a concern. In fact, Sydney Lauer did a study where she looked at Prospector and tried to, do the thing where you create the photometry, get the result out, compare to the original value, and, it was pretty good, but there was significant biases. It did a lot better than sort of standard, assuming typical, just standard star formation histories. Nonetheless, the results were clearly biased by 50%, these sorts of things. Look at these bias values. Virtually no bias at all. Okay, that's nice. Obviously, the sigma is what it is. It's not ideal. Great in stellar mass, not so great in the other quantities. I think these numbers will go down slightly as we get bigger samples. I don't expect them to get much different. But anyway, I thought that was very promising that we can get this. Good. So the last couple of things I want to talk about, I want to switch topics a little bit again because I haven't seen this talked about too much, but I think this is a really interesting problem. JWST has been seeing these very early quenched galaxies above redshift sort of 4. There was one at sort of 4.5 from Adam Carnell, for instance, that are massive, right? So the question is, do we get these in simulations? So here we have to go back to Simba because we don't have Simba-EoR all the way down to redshift 3 or 4. Nonetheless, so we went in Simba and looked for these early quenched galaxies, right? And then this is actually an undergrad student, Jacob Spiele, essentially pick out with the sort of criteria that people had used for selecting these sorts of things and then looked at their history, right? So you can track these galaxies, let's say in specific star formation rate versus age of the universe. And not many, but we see within the Simba 150 megaparsec volume, we see about 30 of these. That number is about half what is actually observed. So we're short by a factor of 2 in the amount that we predict. Okay? That's typical of simulations. That's why it's kind of been, as has been pointed out in several papers. But for those 30-ish, 30 some odd, 35, I think we can look at some of these tracks, right? Specific star formation rate. And the interesting thing we tried to correlate it with was the black hole energetic feedback, right? So we think that black holes are the thing doing the quenching. So how much energy injection do we have from our two main energetic modes of black holes, which is the jet mode and the radiative mode? Remember, the radiative mode occurs in high Eddington ratios while the black hole is growing, and then the jet mode sort of turns on when you get sort of the lower one. Okay, so what we find, this is one example, but it's very generic of how this works, right, is the things that we see are quenched right around redshift 3, so below this line, effectively, in specific star formation rate, roughly, tend to have had a very large phase of growth You can see this in the feedback due to the radiative mode, which accompanies that large growth rate. And so they dump a lot of energy in this, and then the black holes get big. Once they get big enough, the Eddington ratio and the sort of the fluctuating black hole accretion drops, suddenly the Eddington ratio goes down. It switches over to the jet mode, and the jet kicks in and sort of finishes the job, right? Does the final coup de grace and really quenches the galaxy, right? And this is very generic for how these galaxies quench. So we have a rapid phase of black hole growth followed by a drop in the accretion rate, which then goes to a more energetic form of feedback, even though the black holes aren't growing that much. Remember, the jets have very high velocities, so their 1/2 mv squared is much larger than the radiative mode, right? But here's the thing. Virtually all of these things at redshift 3 rejuvenate, right? Something like 85% of the galaxies end up rejuvenating. And so, we have a whole bunch of plots. I don't have time to show all of them about how long things quench. As you go down in redshift, they quench for a longer period of time, and then by the time you get to sort of below redshift 1, most of them just quench forever, or at least until today, right? So there's a very rapid evolution in that. It's kind of cool to look at what this depends on. So this is a UMAP plot. This is sort of a self-organizing map, machine learning. And what this is this is a UMAP of all the galaxies at redshift 3. And the UMAP tries to essentially group them into categories. And then you can go later on and say, what do these categories correspond to? So for instance, in this category, we can color code things by satellite versus central. And you see this grouping is the satellites, this grouping is the centrals. Here's our quenched galaxies. So you see here's our little 30 quenched galaxies down in this region right here. Not many. But you can see what it corresponds to. Obviously, it corresponds to low specific star formation rate, low H2. That's not surprising. What's a little more surprising, it does correspond in general to lower rotational support. So, but not uniquely. There's plenty of other things that have low rotational support that are not quenched. By far, the best correlation is with the black hole to stellar mass ratio. So it's the things that are quenching are the things with the biggest black hole to stellar mass ratio at that time. One thing that was surprising to me is very uncorrelated with local environment. You might have thought these things would live in the most massive environments, the protocluster. No. And in fact, these things are not even the most massive galaxies around. They tend to be sort of intermediate mass. Okay. That just shows that the black hole mass is the thing. So, so that's basically my talk. Cosmic Sands talked about. I think it's a very interesting new suite. They're exploring various aspects of the dust evolution, in particular these sort of ULERGs that are seen. Simba-EoR, I think, again, anybody is interested in comparing their data or whatever to this, please just let me know. We're going to put this on the internet soon. We actually have more disk-space issues than anything. That's our big problem. And then machine learning, and I talked about these early quenched galaxies. Cool. That's it. Thank you.
Hi, Romeel. I'm Sebastiano Cantalupo. Can you hear me? Yeah. Very nice talk, many interesting topics. So my comment is about the AGN feedback halo evocation. So this was more like in the CGM session, but I think it's good to discuss it also now. So you say that there are no observations ruling this out. Well, actually now we have some from the Lyman Alpha Nebula around quasars. Now we know that we need gas in these halos. It will make the problem even worse if you have a very low baryon fraction, especially if there is a low cold gas fraction. This applies to redshift 3 and above. So I don't know if this plot refers to redshift 3. No. We also see it happening for radio loud quasars, radio galaxies. So I don't think it's just a question of the radio mode. So of course this could happen in reality, but then we will need to make even the CGM more turbulent. We need additional mechanisms to make the gas looking.
Yeah, sorry, I should have mentioned. This is all at redshift 0. This only applies, this only starts in really below redshift 1-ish, 1.5. Once you get above that, the big jet AGN are not on for the most part. I mean, you get them occasionally, as I showed you, but but they're very rare. But I think it's interesting to look particularly at the quasars at redshift 3 and see if they show this effect, which we haven't done. So that would be interesting.
Okay, well, we have the last question. Quick question, can you?
It's Laura Schultz-Diaz. So I have a question regarding the early quench galaxies at redshift 3. So just curiosity, do you have like also look at the morphology, like the evolution of if they have experienced morphological transformation, and also the evolution of the rotational support parameter?
Right.
And metallicity?
So this is the rotational support parameter for these galaxies. And so you have to basically match up these little folks over here. And you see they are low rotational support, but not uniquely so.
No, I was wondering, like you have the evolution with time, so you see that
Yes.
they rejuvenate. So how
Yes.
does the other parameters change with time?
Yes, so we have looked at that. So the rotational support was already low for these more massive. It really sort of tracks more with mass than it does with the quenching event.
Okay.
And I think that basically a lot of those low rotational things went through a quenching phase, and now they're rejuvenated, right? Because we only took a snapshot at redshift 3.
Okay.
So we suspect that a lot of these things go through a little.
Okay, and morphological-wise?
Well, it's a little hard at Simba resolution to do that. I mean, to the extent, the thing we found best is to correlate with morphology, as Kappa wrote.
Okay, thank you so much.
Let's thank the speaker again. So, sorry, I saw many hands, but please take the questions to the lunch. Our next speaker is Jonathan. Okay, the stage is yours.
Yes, so hi everyone, can you hear me? Yeah, so I'm Jonathan Stern, I'm faculty at Tel Aviv University.